Hello everyone, my name is Blake Holman. I'm a computer science undergraduate from Kansas State University, and I'll be presenting my research towards home area network hygiene, device classification, and intrusion detection for encrypted communications. The co-authors are Joy Hauser and Professor George Almarakai. In this presentation, I will provide you with the problem overview, discuss some of the related work, address our proposed solution, then I'll explain the details and the result of our experiment. Lastly, I'll explain our conclusion and where we can take our research in the future. Let's begin with the problem overview. First, I'd like to discuss the motivation behind our research. Depicted on the slides is a very simple home network. On this network are common household IoT devices, such as a mobile device, a laptop, a desktop, a TV, and an Amazon Alexa. However, there's always a threat of a bad actor, whether it's a neighbor trying to use your Wi-Fi, a hacker trying to gain personal information. Wherever the case may be, we obviously want to know about it. However, a lot of intrusion detection currently focuses on specific types of intrusions. This can make it much easier for a bad actor to exploit your network. Our goal is to find and prevent these bad actors from exploiting the network no matter what type of attack is occurring. More specifically, our research focuses on capturing the packet traffic between devices on a network. We use this information to determine what types of devices are on the network. Then, after we know what specific devices are on the network, we can determine when a new device is introduced or when a device is not acting the way it normally would. For our research, we specifically focus on packet length and time between packets for a given device. This will be explained in greater detail in a later slide. It is also important to note that we do not use any MAC addresses or IP addresses to identify any devices. For our research, we had three main end goals. Our first end goal was to classify a device when some of the packet information from that specific device was present on the network. Our second end goal was to classify a device when a same type of device, but not the same exact device, is present on the network. Our third goal and our last goal was to determine when a new device type that is not previously represented has been introduced to the network. Next, I'd like to discuss the requirements for our application to run on your network. First, you'll need a wireless network with IoT devices connected to it, and you also need a software tool for capturing the PCAP traffic files from your wireless network. You'll also, of course, need our application. Now let's move on to the next section. In this section, I'm going to discuss some of the research that has already been done on the problem that we discussed previously. In the past few years, there has been quite a bit of research done regarding intrusion detection. However, often this is very specific and only detects one type of intrusion. Most of the research we reviewed specifically analyzes networks for a distributed denial of service attack. In the article, Network Packet Classification Using Neural Network Based on Training Function and Hidden Layer Neural Number Variation, the authors discuss their approach to DDoS detection. They extract packet information and input it into a neural network. They use this information to train the neural network to determine when a DDoS attack is or is not occurring. The researchers were able to detect if a DDoS attack was occurring with a reasonable high accuracy using this approach. The issue with this approach, though, is that it's only relevant for a specific type of attack because of its binary classification. However, from this article and similar articles, we were able to confirm that extracting packet information can produce high accuracy rate for intrusion detection problems. Some intrusion detection research we found does focus on multi-class classification. Using this method provides the ability to determine more than one class of intrusions. Once again, this method also focuses on using network packet features to train an artificial neural network. In a research paper titled An Artificial Neural Network-Based Intrusion Detection System and Classification of Attacks, the authors focus on identifying multiple intrusions. With a neural network training on packet feature information, they are able to produce accurate results. Specifically, they use packet features from traffic data such as the duration of connection, protocol type, total bytes sent. They extract a total of 41 features for each packet to train the neural network. Even with all these features extracted, they are only able to identify a few specific types of intrusions. Although this method does allow for a more specific intrusion detection, some of the research suggests this approach led to a less accurate conclusion. Furthermore, both the single and multi-class intrusion detection system both lack the ability of identifying intrusions that aren't in the dataset previously. For this, we need anomaly detection. Anomaly detection is a method used in intrusion detection that monitors the network for unusual behavior. This technique still uses packet information to monitor the network. This technique is more complex, but if implemented correctly, it leads to a much more versatile approach in intrusion detection. In the article, Network Traffic Anomaly Detection Using Recurrent Neural Networks, the researchers focus on packet traffic between devices on a network. Specifically, they focus on collecting all raw traffic flow data between two IP addresses for an hour. They input normal network traffic data and traffic data during an attack into a recurrent neural network and train the neural network to recognize normal and abnormal traffic behavior. By doing so, they are able to identify when a device is acting abnormally or when an anomaly occurs. We use a similar approach to determine intrusions on a network. In this section, I'll explain our proposed solution to this intrusion detection problem. The first thing I want to explain is how we propose to extract the data. We start by capturing the packet information from a network in the form of PCAP files. Then we break down the files into a readable format and categorize them based on which device sent them. With this organization set, we can break down the packet information even further. First, per device, we group each packet into a 60-second time interval that we call a conversation. A conversation starts with a packet being sent and ends 60 seconds later. In these conversations, we record the length of the packet being sent and the amount of time between that packet being sent and the previous packet. For this reason, we assume some devices will send small packets faster, or small packets slower, or large packets slower, or large packets faster. We believe that this alone can differentiate between device types. However, when we produced these conversations per device, we noticed we had some device types with less conversations than others. In order to make the conversations equal across all device types, we used a synthetic minority oversampling technique to produce synthetic data. On this slide, I pulled an example of what our conversations look like after our data is extracted and our conversations are produced. The number on the left shows the conversation number. Next is the class the device belongs to, followed by the specific device and conversation number within that device. Lastly, we have the conversation data. The first number in the brackets represent the packet length, whereas the second number represents the time since the previous packet has been sent. This is only for a 60-second time period. You can see on the slide that conversations 1955 and 1957 are conversations from the same class and same device. Furthermore, the two conversations look similar. This is important in order to produce the best accuracy with this type of data. You may also notice that conversation 1956 is completely different. It is a much longer conversation with varying packet lengths and time differences. It also belongs to a different device and class than the other two on the slide. This helps differentiate between devices and classes. These conversation sequences will be input into the neural network. In our solution, we use an artificial neural network to classify each device type. Specifically, we use a long, short-term memory recurrent neural network. We input the packet length and time between packets into the neural network. This is input in sequences of conversations. We use the LSTM RNN because our hope is the neural network will be able to remember the differences in conversations between device types. In the end, the neural network should produce what device type a given conversation belongs to. Lastly, we propose making boundaries for each device type in order to determine when a new device is introduced. Take the below graph for an example. In this case, we have a network with two different devices already trained. This is represented by the y-axis device 1 and the x-axis device 2. The blue dots are representing device 1, whereas the red dots are representing device 2. The dots themselves are representation of what the neural network output will be. For an example, if the conversation goes through the neural network and outputs claiming it's 80% like device 1 and 20% like device 2, it will be listed at 0.2 on the x-axis, and 0.8 on the y-axis. Knowing this, we can create a boundary line where most conversations fall for a specific device. Then, when a new device is introduced, take the green dots for example, hopefully this will fall outside the boundary line. This will help us to identify new devices or intrusions on a network. In this section, I'll explain the details of our experiment and the results. The experiment began with approximately 6 gigabytes of PCAP data from many different devices. The dataset contains 3 cameras, 2 Google Assistants, 2 Amazon Echoes, 1 Apple Assistant, 1 mobile device, 2 smart outlets, 1 speaker, 1 clock, and 1 smart home hub. With these devices, we made 9 device type classes. They are listed on the slide. The largest number of conversations for any device type was approximately 133,000 conversations. Using SMOTE, as previously explained, we created synthetic data for each of the device types to match the largest number of conversations. Therefore, each device type ended with about 133,000 conversations. Now I'd like to explain the specifics behind the artificial neural network that we used. Specifically, we used the long short-term memory neural network that was explained previously. The input size was of 2 nodes, and this was for the time between packets in a conversation and the packet length. This was given in a sequence of conversations. For the hidden layer, we used 2 hidden layers of 18 nodes each. This is twice the size of the number of device types that we had. We also tested many other different sized hidden layers as well as many different sized nodes, and this worked best for our situation. We had an output layer of 9 nodes, and this is because there's 9 different device types. We trained on 80% of the data, and we tested on 20% of the data. Now let's talk about the results of our experiment. Note that this graph is read vertically and the bold numbers are the correctly classified conversations per device type. You can see the Google Assistant classified about 16,492 conversations correctly, where it misclassified about 14,000 conversations. The best accuracy you can see is the Smart Home Hub device. This accurately classified 29,359 conversations out of the 30,000 conversations tested. You can also see the least accurate device was the Apple Assistant. This classified only 12,000 out of the 30,000 conversations tested correctly. Now let's talk about the results more specifically. In the training rotation, we started with a 32.44% accuracy rate and ended with a 69.25% accuracy rate. For the testing rotations, each device type had 30,000 conversations tested. This is shown on the table on the slide. The most accurate device was the Smart Home Hub, and this classified 97.86% of the conversations correctly. The least accurate device was the Apple Assistant, which only classified just over 40% of the conversations correctly. After running many different tests and analyzing the results, we can assume a few different devices produce similar conversations. This will cause our neural network to improperly classify one or more devices with similar conversations, and is mainly responsible for the relatively low accuracy. For example, in the table under device type Apple Assistant, we can see the neural network correctly classifies a smaller portion of the total conversations tested. It classifies some of the Apple Assistant conversations as a mobile device or another assistant. Therefore, one can assume that these two device types can act similarly and produce similar conversation data. Knowing both an Apple Assistant and a mobile device can be connected and conduct similar operations if they are both doing similar actions while the data was captured, both device types would have similarly looking conversations. We also noticed that devices that are more often interconnected with other devices, such as a mobile device, speaker, and the assistants, are more likely to produce less accurate results. This may be because of the similarity in the conversations between interconnected devices. We can also notice that devices that are less likely connected to other devices produce the best results. For example, the smart clock is a more accurate device and it is the least interconnected device. As explained in a previous slide, we had 3 tasks we wanted to accomplish. Our first task was to classify a device when some of the packet information from a device is present on the network. For this, we had the Apple Assistant, mobile device, speaker, smart home hub, and clock devices that all contained only one device per device type. As you can see, the smart home hub had the highest accuracy rate with 97.86% of the conversations classified correctly. The next highest accuracy was the smart clock with 93.79% accuracy. Next, the speaker had an overall accuracy of 63.02%. This was followed by the mobile device with 61.39% accuracy. The worst accuracy from task 1 and overall was the Apple Assistant, which classified with an accuracy of 40.02%. Most of the devices classified the majority of the conversations in the correct device type. However, the Apple Assistant device type did not follow this pattern and had the worst accuracy rate of all device types. This task had the most diverse results. The next task we wanted to solve was to classify a device when the same type of device, but not from the same exact device, is present on the network. For this, we had the Google Assistant, Amazon Echo, camera, and smart outlet device types that all contained more than one device per device type. This means other devices of the same type were used to train the neural network. First, we had the smart outlet device with the highest accuracy, that was 76.81%. The second highest accuracy was the camera with 68.92% of the conversations correctly classified. This is followed by the Amazon Echo with an accuracy of 64.30%. Lastly, the most inaccurate device for this task was the Google Assistant, which had an accuracy rate of 54.97%. Each of these device types classified most of the conversations correctly. One can conclude the more devices per device types that are available for training, the more reliable the results are. Overall, this task produced better and more consistent results than the device types in task 1. The last task we wanted to solve was to determine when a new device type had been introduced to the network. For this, we created boundaries that was explained in a previous slide. These boundaries allowed us to determine whether a new device type was introduced to the network. Unfortunately, for this to work properly, a higher accuracy than what was obtained from our neural network must be produced. In this section, I'll talk about our conclusion and the future work for our research. In our research, we introduced a new mechanism for classifying devices on a home area network that relies solely on the sequences of packet lengths and inter-packet pauses that define conversations. Given the nature of the data, these experiments show encouraging results, although far from ideal. For this reason, we propose that such classification mechanisms be used in conjunction with other classification methods that use richer data with more attributes mined from the network traffic. For future implementations on this project, first we must improve the overall accuracy. There are a few different ways to do this. First, one can attempt to improve the synthetic data produced. Another option is to use different devices and PCAP data to train the LSTM. One issue might have been the lack of diversity in the training set, which could have caused a less accurate result. Also, the simplest solution would be to adjust the hidden layers and iterations of the LSTM. Changing the number of nodes in the hidden layer, number of hidden layers, and the number of iterations through the LSTM could potentially improve the accuracy. These are all options we might pursue to produce a more accurate result in the future. As stated earlier, one potential issue with the neural network producing inaccurate results could be the interconnectivity of the data. By using data that we know will not interfere with each other and not have similar conversations as other devices, we may be able to produce a more accurate result. One can reasonably assume this because the device types that are interconnected with other devices tend to have more inaccurate results. By eliminating these bad results, we hope that we can achieve a better overall accuracy. Thank you for listening to this virtual presentation. If you have any questions about any part of the presentation, feel free to reach out to myself or either of the co-authors Our emails are listed below. Thanks again for listening.